All right, guys. So when we're dealing with optimization, so we're still working with optimization. Now, optimization, it stinks. Optimization, it stinks in the regards that it can include anything related to geometry. And I mean anything. So one of the things they like to do is they like to do stuff like this. So it says a rectangle is inscribed inside of a sine curve, and find the largest area that the rectangle can have, and what are the dimensions of the sides. So if we kind of take the idea of a sine curve here, and I actually drew that halfway decent, and we just look at, let me go to draw here. Where's my draw? There it is. And we just look at this idea here. So we're just going to draw straight across right there. And so what they're saying is we're going to, let's see if we can do this right here. We're going to have this rectangle inscribed inside like that. So it's a little bit off, but that's the idea. So the idea is that you're going to, oops, it won't let me. Yep, let me get that out of the way. Nope. You're going to have this rectangle inside of that. In fact, I don't like that at all. So let's just get rid of that. All right. So that's the idea behind it. You're going to have a rectangle inscribed on that one. So if it can be anywhere here, it can be like all the way over here, and it could go all the way across like that. That could be one option, or it can be this skinny one right here that is inscribed just like that. It could be anything. We're not going to worry about, because this side's kind of useless to us because it just gives us the same idea, because the top and the bottom are reflections of each other. So we'll Control C, and we'll just erase a little bit of that. I'm just gonna erase a little bit. It's gonna let me do that. Okay, so we'll just stick with that right there. All right, so let's just kind of see how this works. So if I'm going to take this piece here and we're going to kind of enlarge it here, we know that this is our y. This is our y-axis. And we know we have an x-axis down here, and this is our x-axis. And we know it starts at 0, and it goes up and works down. And we know that crosses, if you know your trigonometry, that's at pi. So we know we go from 0 to pi. So we're going to take some random rectangle, and let's just do it in rainbow just because we can. So we've got some random rectangle. Still can't draw vertical lines. Let's see if I can draw this one better. Nope. So we got some random rectangle that is here. All right. So what we have to find out, though, is that if you notice, these points here, let's call this one point P, and let's call this one point Q, right? Those are going to be, the coordinates on those are going to be dependent on where they're at on the graph. So if P was up here, the X would be bigger and the Y would be bigger. But if it was over here, the X would be smaller and the Y would be bigger. So we have to come up with coordinates in terms of what? So if we look at this, we know, let's just pick point P right now. So we're going to start with point P right here. So we're going to find out what point P is. Well, we know that this is the x-axis, and we know to get to right here is some value of x. We don't know what it is, but we know it's some value of x. So this coordinate right here is x of something, right? So now when we're looking at this, we'd have to deal with the height. So we need to know how high this thing is right here. Well, that is based on the y-axis. Well, the y-axis is really going to be an f of x, but we know what our f of x is because they said it was the sine graph. So our f of x really is equal to the sine of x. So if I plug in x to the sine of x, I get the sine of x. So that's my point here. So my y value is dependent on two things. It's dependent on whatever x value I put in there and the fact of the output that I get from the sine of x. So that is our point P. Now, when we're dealing with point Q, it comes a little differently. So I'll do that one in green. So we're dealing with point Q here. So again, our height is still going to be related to f of x. So we know our height's always related to f of x. So we've got the sine of something. We don't know what it is yet. So we've got the sine of x, right? But we don't know what x is because x is different. It can't be the value of x because we've already used that here. Now, the thing about the sine graph is you know that if I'm working with a rectangle, this has to stay the same. And that means that our values here have to stay the same. So it pretty much makes these things symmetrical. So if I look at this, I know that I have an x over here. All right? So I know that this point here has to be pi subtract the x value. Oops, subtract the x value. That's my x value. So we have pi minus x. Because the sine graph is so perfectly symmetrical here, we know that if I come in x over here, I have to come in x over here. So if you really look at this, this is 0 plus x. So that means this has to be the endpoint pi minus x. That's how I came up with that value. All right, so now that gives us something to work with because they want the maximum area of a rectangle. Area max of a rectangle, which we know is our base times our height. Well, our height is going to be our y value. So now we're working okay with that. So we know we've got the sine of x here. That's going to be our y value or our height. The base is a little different because the base is going to be whatever the value is between here and here. And so if we're finding the value along the x-axis, the x value, you're going to take your right point minus your left point. So our right point is this, which is pi minus x. And then my left point is going to be minus x. So my base, so this was the right point, and this was the left point along the x-axis. So my base has to be pi minus 2x. All right, so now, got something a little different here. So now I've got my f of x. This is my f of x for the area. We'll just call that area. So I've got f of x for the area is equal to my base, which is my two endpoints subtracted, times the sine of x. So now if I look at that, I've got two functions, so therefore I have a product rule. So we can call this one U and this one V. And so we're going to do the product rule for f prime. F prime of x is equal to, I'll take the derivative of this one, which is going to be negative 2 times V, subtract the derivative of sine, which is cosine, cosine of x, multiplied by pi minus 2x. So we get to this point here, and we should be able to find our maximum here. This is our first derivative, so this is going to give us our maximum if it's equal to 0. So if we set this thing equal to 0, f prime of x, this does not factor well. You can't solve this. So if it won't solve, use graph of f prime of x where it equals 0. So we're looking for the x-intercepts. So if you take this piece here and you put it into your calculator, so if you have a TI-83 and you plug in pi minus 2, I'm sorry, what am I doing here? If you plug in this to your calculator, negative, you can even do it into Desmos, sine of x minus cosine of x times pi minus 2x. If you put that in your graphing calculator, it's going to take you on a little journey, and you're going to find that, where did I write it? That the only usable x, or where it's an x-intercept, is going to be, it's going to come across like this, something like that. And right here, your x-intercept's going to be right around 0.704. It's a 7, guys. 0.704 and 0. So that's what my x value equals. My x of my maximum is equal to 0.704 based from the calculator. So remember, this is from the calculator. So you got to graph it. You got to be able to use both. So then if we take that and we plug our x value back in here for the maximum area, let me move this up again. The maximum area is equal to pi minus 2 times 0.704 times the sine of 704. And that is going to give you a value of about 1.12 square units. 1.12 units squared. So, and your dimensions are going to be 0.704 by 1 point something. So we're going to take, because our dimension here, our dimension on the bottom is going to be pi minus 2 times 7.04, which I believe is like 1.7-ish. So it's 0.704 by 1.7 something. Because if this is 3.14, that's 1.4. Yeah, it's going to be right around 1.7. I don't have a calculator right here, so right around 1.7. So again, you can tackle things a little differently. The inscribed circle one is a little tougher. So just keep working with them, guys. Remember the inscribed circle, you're dealing with f of x. So the inscribed circle is really pushing the f of x idea. All right, so let's do one more here. I don't know if you guys remember it a while ago, and I don't know what happened to it. Let's see what happens. Don't know where my extra writing went. All right. Well, basically, it's the idea of this. We have a flat, let's just call it a flat sheet of cardboard. We did this in Math 2 Advanced cardboard. And it's 20 inches by 25 inches. And we're going to make an open topped box with maximum volume. So again, it's anything geometry wise. So let's just take, I'm going to draw you guys a real box this time because I can't draw still. So let's just take that, for instance, right there. Change the color a little bit so we can see the difference between the two. So we know that this is 25 and we know that this is 20. But we've got to make a box out of it. So we're going to fold the ends up like this so we can cut around the edges and we can fold and make a box along the edge like this. So then what our box looks like is something like this. So the idea is this, guys. So we've taken this flat piece and then we folded these edges up like that. We don't know what the edges are, so those are X and X. And that means this side is X and X because these corners have to be square or the sides are funky looking. So we know what? We know that the new length in here, or the new base, let's say, is 25 minus the two X's that we fold up on the end. So this is going to be 25 minus 2X. Now the width on this side was 20, so it's this middle piece here has to be 20 minus 2X because I folded the ends up. So this side is going to be 20 minus 2X. And the height has to be the X. So if you remember, volume is length times width times height. So therefore, it's X times, doesn't matter what order you put it in. I just like to work smallest to largest, 2X times 25 minus 2X. So now we can work from here because we know that we have we have an x cubed. So we have got to do some multiplying there. Oops. My lights went out, guys. Be right back. So if you multiply this out, you get 12x. So we just do a lot of FOIL here. You're going to get 12x cubed. And then you're going to get, I'm sorry, 4x cubed. Backwards. I looked too far down. You're going to get, because you can factor some things out, move some stuff around, and you're going to get 4x cubed. And you're going to get minus 90x plus 500x. That's 90x squared, though. 90x squared. So that's my actual volume. Oops. We want volume of x. So now I want the maximum volume, so therefore I got to do v prime. V prime is equal to 12x squared minus 180x plus 500. So I took the derivative of that. Now again, if you're having trouble finding these pieces, you can either you can graph again. You can use the calculator and look for zeros. Zeros of v prime. Don't forget to look for zeros of v prime. So where v prime equals 0 is at a couple of different spots. And you have two different spots. One is approximately x equals to 3.7, and the other one, x is equal to 11.3. Now, if we go up here and look at this, if I plug in 11, it doesn't work because 2 times 11 would be 22, which is longer than this side. So 11 is not going to work. So don't forget. So 11 is no solution. It's too long of a side, right? Because this whole side was 20. So if this side becomes 11 and this side becomes 11, that means that side has to be 22. Doesn't work. So we're okay with that. I'm okay with, we're not going to use this one at all. So that means my x has to be 3.7, which is equal to the height. And then I also have 25 minus 2x, which is 3.7. And that's going to be equal to my base. And then 20 minus 2 times 3.7 is equal to my height. And when you find those, that'll give you your actual volume, your actual dimensions. And then you would use these dimensions to find your actual volume. And your actual volume ends up being 820.5. So if you do the math here and you multiply these out, you get 820. Approximately 820.5. And I don't remember, is it in inches? Yeah, inches. So inches cubed. So again, first derivative and volume. All right, I shouldn't say volume. First derivative and anything geometry. Okay. All right, guys. Good luck on that. We'll see you soon.